Okay, so the times now is 8:17. So let's continue our discussion topic on SVM. Clear? Boleh dengar? Okay. So before we proceed to discuss the modulation technique for space vector modulation method, so I forgot to state the formula in order to calculate some important parameter. For example, you want to calculate the component of vector using the trigonometric function. So actually for cos theta, for example, the triangular with yellow color here, so you can calculate the V beta, right? V beta. So here you need to apply sine, sine function. So where sine, for example, this case the angle is 60 degrees. So which is the ratio between opposite and adjacent, right? Opposite you divide by adjacent. Is it right? Sorry, opposite divide by hypotenuse. Opposite divide by hypotenuse. Okay, for calculate the component vector here, right? So you need to apply the sine function. So where the sine function, cos function. So maybe I write here. So here cos 60 degrees. So you divide between what? Adjacent and hypotenuse. Hypotenuse. Okay, then you rearrange the equation, then you can calculate all the component of vectors. Okay, now we can proceed. Yeah, maybe yesterday we discussed to calculate all the component vector. So where the space vector V, you can also express into a rectangular form. So which has the rectangular part as V alpha and the rectangular part V beta. So here is the V alpha and V beta to calculate the space vector here, the V. So this vector. Okay. So then you get the equation as given in equation 18 and 19. Okay. Is it clear? Okay. So now we proceed to the next page. Sorry. This one discussed already. Sorry, this one. Here is V alpha and V beta, right? V alpha and V beta. Then next page here. Okay, so the space vector, the voltage component. The voltage components can also be written into another form. In terms of the magnitude of space vector. Okay, so remember your space vector. So it consists of the magnitude and angle. So this case, the angle is theta sec. Theta subsets. So you must write in capital letter for the magnitude value. Okay, so the vector has the magnitude and the angle. So you can write into polar form. So where you have So remember your V, the imaginary part is the V beta. So this is the V beta, right? And also the real part is the V alpha. So where your V alpha and V beta, you can express as you have the magnitude and the cost function. Okay. So this is equation number 20. Okay, so you can apply the trigonometry function from here, from this page. Okay. Okay, so sin theta is opposite, divide by hypotenuse. If cos, you divide between the adjacent and hypotenuse. Okay. Okay, so you apply the trigonometry function to obtain this equation, V alpha. And same goes for the V beta. So how about the V beta? Can someone give the answer? V beta, applying the trigonometric function. So the hypotenuse here, right? So this is the hypotenuse. So your angle, so mean your triangular should be like this lah. Okay. So you want to calculate V beta. So the hypotenuse is V, right? The hypotenuse is V, capital letter, the magnitude value of the space vector. Okay. So you apply the sine function, right? Because you want to calculate the V beta, right? V beta. So V beta is opposite. Remember here, and cos theta sec is you divide between which one? V beta, right? V beta and hypotenuse. Hypotenuse is V. Okay, clear? Then you rearrange this equation to solve for V beta. So you have the magnitude V, okay, and sine. So this is equation 21. Okay. Maybe I can write the formula here. Theta sec is opposite. Sorry, cos. Sorry. This one is alpha. Sorry. The alpha sine opposite, right? Opposite is V beta. Divide by V. Orang buat kita tahu sebelah adjacent divide by hypotenuse. Opposite divide by hypotenuse. Okay. Okay, so you apply this equation to get equation 20 and 21 for solving V alpha and V beta. Okay, where here, where the magnitude, okay, maybe I write, where the magnitude and angle of space vector are given by or can be calculated as, how to calculate the magnitude? So you apply Pythagoras theorem. V is equal to square root of V alpha, right? V alpha squared plus V beta squared. Okay, so this is equation 22. And the angle is what? Theta sector, right? Theta sector. Theta sector is arctangent. Sorry. Tangent minus 1. So the ratio between V beta and V alpha. So this is equation 23. Okay? Simple, eh? V alpha, V beta. Sorry, V beta alpha. Okay, you have to take note that the definition of theta sector. So this is the definition of theta sector. So where the theta sector, okay, not that theta sector is the angle within a sector which is ranging from 0 to pi per 3 radian. Okay, so remember the size of each sector is 60 degrees. Okay? So you have mapped all the vectors available in three-phase inverter. You have 6 active. Then this 6 active vector, if you join from one point to one point, as a result, it will form a hexagonal. So the hexagonal you can divide into 6 sectors. So where the sector is equally divided by 60 degrees. Okay. So or you can state that your angle here, theta sectors, is between 0 to pi per 3 in radian. Okay, this is illustration for general representation. So we just state VA and VB. We do not state at which sector the space vector is located. So this is the general representation. You have VA and VB as adjacent vectors. VZ for 0 is as a 0 vectors. Okay, now this page actually mention us you can state the space vector into rectangular form. V alpha and V beta. Okay, now we move to the next page. Okay, this page. Can I copy this blank page, right? I give to you this one is blank page, right? So maybe we can redraw. Now you try to redraw the diagram. Maybe we just revise. So this is your space vector. So remember, this is your space vector. So where your space vector is rotated to form a circular locus, because the system is balanced. So in order to produce the space vector, so you can summing these two components of vectors. So you have the VB here, right? This is just revision. So where this component vector, so actually is your vector VB, you multiply by its ratio, where its ratio is the TB divided by T. So so you have to take note the ratio TB per T. So actually the value always less than 1. Because your T is summation of TA plus TB plus TZ. So that's why when you multiply the ratio with the VB, the magnetic value is 2/3 VDC. So that's why the length here will be shorter compared to the VB here. And so the length means the length is depends on the TB, the time application of for applying the VB. And TB is the time application, time taken to apply VB. Sorry. So where your space vector here, coming between the adjacent vector VB and VA. So here is V, the vector, the component of vector. So you can state the equation as VA multiplied by its ratio, TA divided by T. Ini division. And zero vector. So remember your zero vector is located at origin, where the D and Q component are zero. So means here you have VZ and its ratio, TZ divided by T, where the value is zero. Okay. So means the vector here is summation between the adjacent vector dB per T plus dz per T, right? Okay, so you can write the equation of space vector like this, or you can state use you can rewrite the equation into another form, right? Into a rectangular form, V alpha and V beta. Right? Okay, so you have to take note that from here, maybe I write, okay, maybe here, taking into account that the magnitude of adjacent voltage vectors used in voltage component in equation 18 and 19. So the magnitude value, so means, so remember you have equation 18 and 19, this one, right? 18, 19. Where's the equation 18, 19? Here. Okay, maybe I can copy this equation. How to copy? Here you copy and put to here. Okay, so you have equation 18 and 19. Maybe I put here. Okay. So this is equation 18 and 19. So the magnitude of adjacent vector is this one. This term, VA, VB, and VB. So you must write in capital letter because this alpha, V alpha and V beta are scalar quantities. It's not the vector quantity. So that's why you have to remove the straight line on top of the letter because all the terms are scalar quantities. And to indicate that VA and VB are the magnitude values and the magnitude values. So where the value is constant, right? So where the magnitude of adjacent vector here, VA and VB, so the value is what? Can someone give answer? VA and VB. We have calculate the magnitude value. So the value is 2/3 VDC. Because, so remember this VA, this is the vector, right? So you can write as the magnitude and the angle. The angle is 0 degrees, right? So where here is VA or V. For VB, you have the magnitude VB, right, in capital letter, and the angle is 60 degrees. The angle is different, but the magnitude values are same. So you have to calculate VA. For example, during we discussed for the mapping of the vectors, you calculate the D component of the V1. Remember V1. Mana tadi? V1. This one. V1. Right. So where the V1, the D component is, the D component of V1 is 2/3 VDC. This one. V1. Where is the V1 here? 2/3 VDC. And okay. So we can consider all the magnitude value for each active vectors is 2/3 VDC. 2 divided by 3 multiplied by VDC. Okay, clear? So means here, where is the page? This one is 2/3 VDC. All right. So this is equation. You have how many equation now? 23. Then here is question 24. Okay, then. So you have to, now you can calculate or obtain the on duration for TA, TB, and TZ. So using equations 18, 19, and 24. The on durations for applying or switching BA, BB vector, and zero vector can be calculated. Calculated. The following equations. Okay, so then you apply equation 18 and 19 here. So maybe I cannot move. Maybe I try to copy this equation or move this equation to here. Possible to move? All right. Okay, so you can calculate TB. The time taken to apply VB, voltage vector VB. Actually, you get here is set 3. The sampling period T. Then you multiply by V beta divide by DC voltage. So this is equation 25. So you apply these three equations, 18, 19, and 24, you can solve for TA. 32 VDC. Okay, you multiply the difference between V alpha and V beta divided by set 3. So this is equation 26. And the time taken for applying zero vector is the difference between the sampling period and summation of TA and TB. So this is equation number 27. Clear? So now you can derive this equation for calculating on duration TA, TB and TZ, TZ. You remember this T actually you can get from here where your sampling period is summation of TA, TB and TZ. Yeah, you rearrange the equation, then you get the equation 27. Okay, you try. Apply these three equations, 18, 19 and 24. Right? So trust me, you can obtain this equation, TB and TA. So for example, for calculating TB, so this you apply equation 19, right? You rearrange equation 19. Can you see this? 19. Okay. So where you rearrange equation 19 for solving TB. So where your TB is what? TB. Okay, sorry. Before that, is it okay? Okay, we know that from equation 19, you can write like this, and VB is where your VB is the magnetic value, right? So where the VB value is 2/3 VDC, right? Then you have TB. So sin 60 degrees, sine 60 degrees, sine 60 degrees. So actually the sine 60 degrees. So you can write as what? Sec3 divided by 2. You check using calculator. So the value is when you calculate, you get the value is 0.8666 blah blah blah. And so actually you can write the sine function as sec3 divided by 2. Please check. Is it right? Okay. Okay, good. Okay, then sine 60 you can write as sec3 divided by 2 here. This term. VB you have 2/3 VDC, TB sec3 divided by 2. Then don't forget to there's the sampling period T. Okay. So then you rearrange the equation here, TB. Sorry, the equation to solve for TB. So then you get what? V beta T VDC 32 then 2 divided by sec3. So then you can simplify the equation above. Finally, you get this equation V beta T VDC sec3. Okay, proof. You can prove now the equation 25. Okay. For TA, you try. And try at home. Buat sendiri. Okay. Boleh faham Okay, now you can derive the on duration to switch the vector VA, VB for adjacent vector and zero vector. Apa dia? Okay, any question before we proceed to next page? Okay, this section, you must able to derive the equation for calculating on duration. On duration means on time. How long the time for the vectors to turn on. VA, VB, and zero vector. And TA, TB, and TZ. Okay. So in order to derive, you need to support your derivation with a diagram, the vector diagram. For example, like this one. So you have to indicate all the component vector values. So of course, you need to apply the trigonometry function. Cos theta is adjacent divided by hypotenuse. Sin theta opposite divided by hypotenuse. So you apply the trigonal function to calculate all the component vectors. So then you can proceed to derive. Finally, you get these three equations, TB, TA, and TZ. Okay. Okay, then we go to the next section, the very important section. So remember, you need to understand this one, because you need to do for the assignment. Okay, for this section, switching of voltage vectors. Okay, this case, yeah. Okay, this case, sorry. So let's say we start to analyze the switching of vectors for the case of when your space vector is located in sector 1. This sector 1. So remember, this is the sector number 1. Okay. You have 6 sectors. So when the vector is located in sector 1, so the adjacent vector is what? So you have here is V0, right? VZ, VZ. You have here is what? VA. Or basically the vector is V1. And the first sector, you have V1, here will be V2. So this, in general, you state as VB or V2 vector. Okay, VZ is, it can be either VO or V7. Okay, so remember, zero vector, you have two combination of switching state, 0, 0, 0, and 1, 1, 1. Okay, then don't forget to put the state for each vector. So here the state is 1, 0, 0. Here will be 1, 1, 0. Then you have here 0, 0, 0 or 1, 1, 1. So this point is the origin point for the DQ plate. So your space vector now here. Okay, so this section to describe how the vector are selected. So actually, your controller or your modulator. So maybe I can write here. So your modulator, this is your space vector modulator. Space vector modulator. And your controller. So the modulator is responsible to produce the switching state. So I just put the state for controlling the top switch only, SA, SB, and AC. So the input of the modulator requires the reference. So where your reference is here, the space vector reference. I put superscript star to indicate this variable as a reference or set point. So actually, your controller or your processor, so you implement this space vector using the digital implementation. So where all calculation will be updated at fixed sampling frequency or sampling period. For example, this processor, the sampling period is 100 microsecond. So it will update the data every T. So where your T is 100 microsecond. Every 100 microsecond, it will updated the data. Yeah, means your controller or processor calculate the on times, then do the switching vector mapping lookup table, then finally it will produce the state, the switching state. Then after next cycle, next sampling period, it will update data. Then this process will be repeated. Okay. So the sampling period we can define here T. For example, here your T is 100 microsecond. So starting from 0 second here, then it will end at 100 microsecond. Okay. So let's say now we divide your sampling period T 100 microsecond at this point here. Okay. So means from 0 to this point is T per 2, right? Here also T per 2. Okay. Okay, before I proceed to discuss this one, so remember your space vector, you can write as VA and its ratio plus VB and its ratio and the 0. T. Clear? Okay, where from the above equation, you can also, okay, remember your T, the T is the summation between TA, TB, and TZ. So the equation above you can rewrite as 1 divided by T 2 VA, but this term bracket is TA divided by 2 plus 2 VB, DB divided by 2 and 4 VZ. So maybe this one, I need to put the diagram below here. So here, sorry, VZ divided by what? 4, right? Okay. So the equation above you rewrite. So that you apply ni lah, you try to factorize the equation above, so then you get the below equation. Is it true? Okay. Both equation are same, right? Okay. So actually based on the equation below here, so that's why for this diagram, the timing diagram here, you can notice there are eight intervals. You have 8 intervals. Interval to mean selang. Okay. So you have the first interval here. Maybe I try to 1. Second interval. Third, you have 4, 5, 6, 7, and 8. You have 8 interval for one complete sampling period. T tadi. For one sampling period, you can divide into 8 intervals. Okay. Okay. So based on the equation here, so actually the principle to switch the vectors using we call this one as the approach. This approach is the symmetrical approach. So the first interval here, right? This is the first interval. The first interval and the 8th interval, interval number 8 here, and interval number 4 and 5. So during this time, this interval, you have to select the 0 vector. This is the technique lah, the concept. Sorry, the principle. So interval number 1, 4, 5, and 8, you have to choose 0 vector. So this this selection you need to apply for every sector. Sector number 1, 2, 3, 4, 5 until 6. It means at the beginning of the sampling period, so this case you have to choose, here must be V0, right? Why? Okay. Here must be V0 vector. So maybe I need to erase this. So here in this interval, you have to choose 0 vector. And at the end of sampling period, here also you must choose 0 vector, V0. So where the state is 0, 0, 0, 0, 0, 0. And at the middle of the sampling period, specifically at interval 4 and 5. So this case also you choose 0 vector, but the vector is V7. And remember, you have 0 vector, you have V0 or V7. V0, the state is 0, 0, 0. V7 is 1, 1, 1. You calculate the DDVQ value, then you get 0. So that's why V0 and V7 located at origin. Okay. So second interval, how about the second interval? So this case, you have to choose VA. For the sector number 1, and for the case of space vector is located in sector number 1. So the second interval, you must choose V1. V1 as VA. Then third interval, V2. Okay. So means for one sampling period, at the beginning, the modulator will choose V0 vector first. So mean it will start here, right? Then it will move or jump to V1, number 2, second interval. Then the modulator select V2, jump to V2, number 3. Then goes to V7. Here will be number 4. Right? 4. So you compare with the timing diagram here. Compare V4, V7. Then it will be return back to the V2. So mean it will start again at interval number 5. Here will be V7, right? Means when V4, it will stay for interval V4, for interval number 4 and number 5 at 0 vector. Then at interval number 6, it will jump to V2. Here will be number 6. So mean your vector, dia akan return back to 6. Then go to V1. So here will be number 7. Then finally, at the end of the sampling period, it will back to the 0 vector, which is V0. So you can see how the vector is switched, starting from V0, 1, then move to here, V2, then goes to a 0 vector, V7, then turn back to V2, V1, then finally end to the V0. So this is the way how the modulator switch the vectors for one sampling period. Remember, your punya modulator the modulator will be updated, and the calculation TA, TB selection will be updated for every 100 micro, every T. So during the time of sampling period, the modulator will choose these vectors in sequence 1, 2, 3, 4, 5, 6, 7, 8. Turn back. Okay, so you try to compare with this timing diagram. So means here starting from V0 at interval 1, interval 2, V1, V2, V7, V7 again. Then interval 6 will be what? V2, okay? V2, and here will be V1. Okay? So then we can also indicate the timing information for each interval. So here is T0, right? T0, you have here also T7 or T0. So maybe I just put TZ, boleh TZ. Here also TZ, TZ. So where each time here, the time 0, the 0 time here, you must divide by, because you have 4 intervals. Here must be 4, divide by 4, you also divide by 4. Okay. So for T1, so this case, since your VA is V1, so means TA is equal to T1, right? VB is V2. VB is V2. So mean your TB is T2. Okay. So means at interval number 2, here will be TA. Right, TA. Or boleh dapat TA divide by 2. Here also TA. Because V1, you select V1. You switch vector V1. So here will be TA divided by 2. Because you have 2 interval. And for one sampling period, you have 2 interval for TA. Sorry, for switch vector VA or V1. You faham So for interval number 3, this one will be TB. TB divided by 2. Here also TB divided by 2. So actually, based on this timing diagram, it will fulfill this equation. You can check. For one sampling period, you have 2 times for selecting VA. So that's why here will be 2. Right? So you have 2 times for selecting VB vector and 4 times for selecting 0 vector for one complete sampling period. Is it true? Did this topic something new to you? Okay, this very advanced technique, which is widely used for acid drive system, acid drive application. For example, vector control using direct torque control, field oriented control for controlling the 3-phase AC motor. Okay, clear? So means you can sketch the switching state. So here you have switching state SA, SB, and SC. So where the state varies between 0 and 1. And remember, your state can be either 0 logic or 1 logic. So means you can sketch your switching state. VO is 0, right? So means 0. Here will be 0. SC will be 0. 0, 0, 0, and 0, 0, 0 is V0. And combination state of 0, 0, 0 is V0, which is located at origin at interval number 1. Then when it moves to interval number 2, dia akan jump the modulator switch vector V1, right? V1 kan? So where the state is what? 1, 0, 0. So then your SA suddenly changed from 0 to 1 for this interval. So how about SB? 0, still 0, maintain to 0. SC? 0. Okay. Then it will jump to V2, right? Jump to V2 at interval number 3. Interval number 3 here. So where the state is 1, 1, 0. Is it right? 1, here will suddenly change to from 0 to 1, 1, 1, 0. This one maintain 0. Right. Very interesting topic. So actually the space vector is popular title for final year project. Okay, then V7. Then from V2, it will jump to origin, right? To choose V7. So where V7 is 1, 1, 1. The state is 1, 1, 1. So mean this one is maintained. You also maintain. Then for AC, suddenly change from 0 to 1. Then same goes for interval number 5. Maintain kan 1 because V7, 1, 1, 1. Right. Then interval number 6. This one is V2. Is 1, 1, 0. Here will be 1. Here 1, right? 0. Then for V1, maintain. Here suddenly change to 0. Here maintain 0. Then at interval number 8, this one is V0. The modulator choose V0 vector, V0. So where the state is 0, 0, 0. Nampak dia punya pattern of the switching state. So that's why you can see actually the waveform is mirror, right? The left hand side and the right hand side at the middle point. And so that's why this technique we define as a symmetrical approach. So actually in SVM you have two approaches. One is symmetrical and the other one is asymmetrical. So for this subject, we focus on the first approach, symmetrical. So you can see the switching pattern, the state is mirror for the left and right hand side. At the beginning and at the end, 0. At the middle, 1. Okay. So this is how the modulator switch the vectors for one sampling period within t time. Okay, any question? So this is for the sector number 1. Open. Tak lihat lagi ni. Okay, we try to move for this section, then we can have a break. So sector number 1. Sector, sorry, this one still sector number 1. Sorry, sector number 1. Okay, so this diagram, we want to see the effect of the time or the on duration. For example, for the first case, your space vector is close to the VA. So remember, this is the VA. Right, here is VA or V1. Here will be your VB or V2. This one V0. Okay. So this case, your space vector is close to VA or V1. So what is the effect of on duration? TA, TB, and TZ, TZ. Okay. So remember your space vector, the definition of the space vector, V is VA, TA, T, VB, you multiply by its ratio, and 0 vector, and TZ divided by T. Okay, so in order to plot the space vector V, so you actually use summing and applying this equation, then you can sum the component of vector, or you can draw the component of vector like this. So you have the vector VA calculated by its ratio, right? And you have here the vector here. You need to sketch properly in geometry. So maybe here. So remember, maybe you can project the line first. So where this line is parallel with the VA. Cantik pula. Okay, so this is your component vector. So where the vector here, which is aligned with the VA, in phase of with VA, so this vector is what? You have here is VA multiplied by its ratio, right? Then for this vector is VB vector, you multiply by its ratio. Clear? VB. Okay. So this is the way you sketch the vectors to produce the resultant vector V. Here, this vector. Clear? So to sketch the switching pattern SA, SB, and AC. So from here you can notice that by sketching properly, you can notice that the component, this vector component, where the length of the component vector or the amplitude is larger than this one. Is it right? You have to draw properly in geometrically. So then you can have this component vector. So since this vector here is larger than VB TB per T, so meaning that your TA is larger than TB. Is it right? The term of VA and VB, the magnitude value are same. So VA and VB ni. Maybe I need to, okay. This vector, this term, the value are same because the magnetic value, so you can put the magnetic value where the magnetic value is 2/3 multiplied by VDC. So the only term that difference is time, TA and TB. So this term will determine the length of the component vector. Is it right? So means this case your TA will be, your TA will be larger than TB. So the time taken to select VA will be longer compared to select VB. And because your space vector is close to VA. Nampak dia close means this angle is smaller than compared to this angle. Is it right? So that's why the effect is you can see the interval. For example, this is interval number 1, 2, and 3. Between interval 2 and 3. And also interval 4, 5, 6, and 7. So you can see the difference and the size of interval. Is it right? Because for interval number 2, you need to choose what vector? Interval 2. VA, right? Interval 3, VB. Interval 6, VB come first. Because this is you can have finally you can get symmetrical waveform, kan? Symmetry waveform. So VB, then VA. So means kat sini kalau you compare the interval size, so you can see the interval for TA is larger than TB. So TA is larger than TB. So remember to put divide by 2 because you have 2 times to select VA and VB for one sampling period. So here will be TB divided by 2. Here will be TA divided by 2. Right? So the switching pattern should be like this. Here one, same waveform with the previous. Because the space vector is located in sector number 1. So you can have the same switching pattern. But the difference is the time and the interval size. Okay, for TB and TA. Zero. Here. 1. Okay. Is it okay? My explanation? Understand? So this page, actually I want to highlight what is the effect when your space vector, now the location of space vector is now close to VA. VA or V1. Nampak tak? VA and V1. By sketching properly the component vectors involved to produce the resultant vector of V. Ni yang saya lukis ni, V. So you can have ni VA TA per T and VB TB per T, right? So you need to sketch properly or in geometrically. So by sketching properly, you can notice that this vector VA TA per T is larger than VB TB per T. Nampak? Dia punya length, you compare the length, meaning that the amplitude. So since the VB and VA are same value, the different term value is time, TA and TB. And so mean your time too will determine the length of the component vector. So means your TA should be larger than TA will be larger than TA, ATB. Ni. So that's why your punya interval size, the size of interval 2 and 7 will be larger interval 3 and 6. Nampak? You try to compare the size of interval. So meaning that the time taken to switch vector VA will be longer compared to selecting vector V2. Nampak? Boleh? Okay, so let's see another effect for the case here, case number 2. So the space vector still in sector number 1. So mean here will be V1, here V2, and VZ or V07. So now your space vector is close to V2. Nampak? So in order to sketch to identify the component vectors involved to produce the resultant vector here, V, so you need to sketch properly or in geometrically. So first you need to project this line, where this line should be parallel, right? Parallel with this one. Same angle. So from here, you can sketch the vector, the component vector for this. Right? And another vector, so you need to sketch another line, the projection line. So where this line should be parallel with V1. Ini dah belajar dalam first year subject mathematical kan. Maybe subject apa ni? Vector. Vector diagram ke? So then you have another vector which is here. Right? Ataupun saya boleh state. So this vector as a UA. I put U it's not V, UA. Here will be UB. UA vector and UB vector. So remember, your space vector here is summation of UA plus UB and UZ. I put U because you need for another equation you have to state the punya ratio, time ratio. So where UA is VA and its ratio T. VB its ratio and VZ. Okay. So this case you can notice the length of UB vector is larger than UA. Nampak You can sketch properly. So where your UB, remember your UB is VB TB per T, right? And UA is VA TA per T. So where this term VB and VA, the magnetic value are apa? Same. VA and VB, the magnetic value are same, where the value is 2/3 VDC, 2/3 VDC. So the length is determined by what? Your length of component vector. So of course is the time ratio. Clear? Sebab VA and VB are same. So the term that determine the length of the amplitude vector is the ratio. So this case T are same. So meaning kat sini, since your UB is larger than UA, so based on this equation, you can say that your TB now is larger than TA. Third, TB is larger than TA. Means the modulator switch vector VB, the time taken is longer compared to the time taken for selecting VA. Nampak? Clear? For one sampling period, maksudnya your modulator dia akan choose vector VB for longer time compared to choose vector VA. So that's why your TB is larger than TA. So means here you can see here your TB, the size of interval is larger than TA. And so don't forget to divide by 2 here. Here will be TB, TA. Okay, clear? For the rest sector, for selecting zero vector, TZ divided by 4. I don't need to write lah. Simple ni. Okay, any question? So we study the effect for the space vector when it close to V1. In this case, when the space vector is close to V2. So then you can see the different effect, especially on time, the time, the on duration. Okay, we break for 10 minutes. Dah berasak kepala. Okay, dah sikit gini. Betul lah. Okay, gambar. Nyom. Tak sempat juga habis hari ni. Siapa tak datang kelas? Saya nak pergi ziarah. Ha? Mata-mata saya tahu lah. Balik pada masjid nanti datang ni. Ada pun. Mana Sofian ni pun? Sofian ni. Kita pergi yang ramai. Dan lagi kan? Dan ini je. Dan video. Ya. Jadi saya panggil sekolah lagi. Saya panggil baik. Kalau saya Okay. Right. Okay, last page before we end our class. Hello, hello, hello. Dia tak payah pakai mic. Okay, so For the previous page, we see the effect. Hello. When the location of the space vector is changed. So this first case close to VA or V1. Then second case, dengar? Boleh? Tak dengar? Hello? Tak ada. Hello, hello. Okay, so now we move to last page before we end our class. So based on this diagram, so you can see for this case, your space vector is at the middle between adjacent vector V1 and V2. Is it right? So you can see so we can consider that the angle here, the angle difference between space vector and V1 is, for example, this one θ1. And here, the angle difference between the space vector and V2 is θ2, where θ1 and θ2 are same. Okay, so means what is the effect on your on duration for this case? Is it different or same? The value of TA and TB. So the value will be same because your space vector is located at by angle what? 30 degrees. So this is 30 degrees. Here also 30 degrees. So when you sketch properly the component of vectors to produce V, space vector of V, so then you get here, right? Is it right? Project line. So means here, this vector is V1 multiplied by its ratio. And here will be V2 multiplied by its ratio. Okay, so remember your V1 and V2. So actually you can, the value of V1 and V2, because actually this term you need to write in scalar quantities after this. So where the value is magnetic value. So where the value is 2/3 VDC, 2/3 VDC. So means here your V1, V2 value. And so when you write into, in magnetic value, V1 and V2, so the value are same, 2/3 VDC. So this case, your T1 and T2 will be same, right? Because the length of the component vector are same. Right? Okay, so this is the switching state. So you can see that the interval for selecting V1 and V2, the size are same. And so same goes to here. Okay? This interval for selecting V2 and V1 are same and the same size. Okay, now can you give the answer? What is the effect of on duration if the space vector now, the length or the amplitude will be smaller? For example, so your vector now will be here. Sorry, ke mana nak tulis ni? So this is your, ni. So this is your vector now. New vector, new space vector. So what is the effect on duration? You try reduce dia punya length, the radial component of the circular locus. So now your circular parts will be like this, right? So where your space vector is rotated to follow its circular paths, and where the radial component is smaller compared to the previous. So what is the effect? of the on duration? Can someone give the answer? So before this, your space vector component, sorry, the component of vector is here, V1, T1, P2, T2. So now your resultant vector or the space vector is reduced to this point. So of course, your component vector will become smaller, right? So means your component vector now will be here. And this one, right? You sketch properly in geometrically, so then you can get the component vector. So means here, so remember here is V1, V2. So means this component vector is V1 multiplied by its ratio, and here will be V2 multiplied by its ratio. So don't forget, you must have the zero vector here, VZ. VZ divided by T. Okay. So what is the effect of on duration? TA, T1, T2, and T0 or T7. Okay, the amplitude will be reduced, but the space vector, the angle are same with the previous. So angle are same, and angle ni 630 degrees. So you expect the T1 and T2 also same, right? Is it right? Because the length of component vector V1, T1, and V2, T2 are same. So means your T1 and T2 will be same. So what is the term? And the term of variable that can reduce the amplitude of the space vector. Apa? T1, T2 same. So macam mana you nak make it the reduction of the amplitude of the space vector? Kenapa? Apa? So refer to this equation. Senang betul-betul this equation. You have to plot the space vector, you have V1, T1 divided by T. Then you have V2, T2 divided by T. Then you have zero vector and VZ, VZ per T. So this case, T1 and T2 are same. So how you can reduce the amplitude of the space vector? Amplitude. So means here, your V here, angle is 30 degrees. So this case, you have the time taken to switch zero vector will be shorter or longer? Shorter or longer? Shorter. Kalau shorter means your TZ value is small value. To reduce the amplitude of the space vector, so you must increase the time for selecting zero vector. So mean your TZ will be larger. Why larger? You boleh imagine your vector, the modulator switch the vector starting from 0 first, then jump to V1, then jump to V2, jump to the origin, zero vector, V7, then turn back and V7, V2, V1, and finally V0 for one switching period. So the time for the vector stay at origin will be longer, but the time for the vector stay at active vector will be shorter. Maksud dia duduk kat sini masa dia singkat. And the time taken for the vector, sorry, the modulator to switch adjacent vector V1 and V2 will be shorter compared to the time taken when the vector stay at origin. Clear? So means this term will be significant. So means here, kalau you try to sketch the waveform, so remember the interval that to choose the zero vector, so at the beginning, here, the beginning kan, interval number 1, at the middle, interval number what? 4 and 5, and at the end interval, 8. So means you can imagine now, the size of this interval, 1, 4, 5, and 8 will be wider. The size will be increased lah. Okay, so maybe bila you try to sketch, so let's say, yeah, maybe I try to project the line first. Here, I think should be here. This one. Okay, so starting at the beginning, so it must choose zero vector, and starting from origin, right? V0. So V0, the state will be 0, 0, 0. Ini interval number 1. So interval number 1 here. So you punya interval will be wider, and dia akan jadi lebih besar. And the size will be larger. Interval number 1. So then this is interval number 2. So then the states SA will be switched from 0 to 1. So this one maintain. Maintain. Then it will switch back to 0. For SB, here 0, right? Then suddenly switch to 1 until to this point, I think, this point. Then switch to 0 back. Here, 1. Okay, and now you can see the difference. Okay, so the 0 vector, where is the interval to choose 0 vector? Here, right? 0, because 0, 0, 0 state, and at the middle, here 0 juga kan, 0 at the end of the sampling period, at the middle, 1, 1, 1 kan, 1, 1, 1, so means here. Is it right? Interval number 1, 4, 5, and 8 for selecting 0 vector. So the size of interval will be expanded. Is it true? But the time taken for selecting adjacent vector V1 and V2 will be shorter. Shorter kan? So this will be shorter. This for selecting T1 kan? T1. Sorry, T1 per 2. You must divide by 2 because you have 2 times. For one sampling period, you have 2 times for selecting V1. Maybe I write here like T. Here, this one. Sorry. So here, T1 divided by 2. And this interval, T2 divided by 2, right? This one, T2 divided by 2, and this interval, T1 divided by 2. So the size of the interval for selecting adjacent vector V1 and V2 will be smaller compared to the above. Nampak? Kalau kat sini above, your size will be expanded. Because you want to produce very a longer amplitude of the space vector. But the interval for selecting 0 vector, small size. Yeah. Okay. So actually it always fulfill this equation. Boleh buat soalan quiz ni. Maybe next week. I give some cases, then you need to scale the component of vectors, the switching waveform, and then include with the timing information, TA, TB, and divide by 2 or divide by 4. Okay. Okay, so maybe we can proceed our class. So class next week we conduct via online using Microsoft Teams. Okay. So maybe we just discuss last section here. Then we can discuss on exercise, one exercise here. Okay, that's it. Thank you. See you next week.